And I would now like to invite Dr. Reuth Mirsky. Dr. Reuth Mirsky is a senior lecturer. Dr. Reuth Mirsky is a senior lecturer at the Computer Science Department in Ilan University. Her research is all about human-oriented AI and robotics, and her lab's main focus is on developing a robot to help the blind. Her lecture's name is quite exotic, I have to say. It starts ordinarily, goal recognition as reinforcement learning, and then fantastic goals and where to find them. Dr. Mirsky, please join us.
I think that the last time I've been to this hall was Noor Shocher Mada, so it's been a while. So today I'm going to talk about goal recognition, reinforcement learning, fantastic goals, and where to find them. So I'll start generally with the problem of reinforcement learning. In this session, I guess I don't need to formally introduce this setting, but I will just to make sure we're all aligned here. We have an environment, we have an agent. The agent acts in the environment, we have actions, go into the environment gives us back state and reward. And we need to somehow optimize what the agent does in this environment to optimize the rewards. And improving means that the agent was able to get better rewards. But how many of you designed an RL agent, by the way? Okay, so many of you know this procedure and are you know how challenging this might be. How many of you struggled with a problem where you didn't really had to maximize a reward, but you actually wanted to reach some goal? Okay, not all RL problems are goal-directed problems, but some are. And then we have this weird mix about when we talk about rewards and goals, and Professor Mansour just talked about how challenging it is when you have a delay in your reward. So think about a task for an RL agent where you only know what you wanted to do or what you need to do if you are able to reach the end of the task. That becomes a very challenging problem to solve. And there's a whole line of research that talks about goal-directed reinforcement learning. And basically what they do is, like most learning problems, we identify a problem, we construct a data set, we train a model, we evaluate it, and if you're in academia, you publish a paper. If you are in industry, you raise some funds. And that's it, and most of the time that stops there. You don't really get to leverage what you've learned. Most of the times we talk about problems, like Professor Mansour mentioned, we still don't have robots that are capable. We don't have robot control that we can use reinforcement learning for. Navigation, robot manipulation, mostly in lab settings, Mujoko, Minecraft, these are the types of problems we are able to solve right now. And in the last Europe's conference, I've been to the goal-conditioned RL workshop. There have been 31 papers. 13 evaluated their work on navigation domains in simulation, 11 on manipulation and locomotion, only 3 on real robots. The others were in simulators. 4 gameplays, Atari, Minecraft. Only 3 notable ones had real-world application at the end of their process. One was medical decision support system, one was selecting which explanation that the system outputs we can use, and one was about parcel routing in multi-agent systems. So this is a really challenging problem when we try to solve RL as is, especially RL for goal-conditioned problems. And I argue in my research that often we don't really need RL to be reinforcement learning. This is not what we really want. Sometimes RL is just the means, it's not the goal. So, mind the pun. So, if you think about it, for example, when you have autonomous vehicles, you want to understand the goals of other vehicles around you. So you know when someone's about to bypass you. When you have service robots, you want to know how to be a nice assistant and help people coming into your store. The Da Vinci robot that operates needs to understand what's the intention of the physician so it can assist it without making any mistakes along the way. Also for adversarial purposes, if someone attacks your system, you want to understand what they're trying to do and how they're trying to accomplish it as well, because you want to intercept that. And if you have a robot in a jam session with you, you would like that robot to be able to understand where your music is going so they can jam with you and they can make a harmony together with you. So in all of these settings where we imagine RL be useful, basically one of the things we really care about is that they require theory of mind. We need to understand not what policy we need to be performing, but what is the goal of the agent in front of us that we need to understand so we can become better agents or better collaborators. So I'm interested in a slightly different problem. We'll talk about how it relates to RL in a second, but I'm looking at goal recognition, where the task is to infer the goal of an agent given observations in a database of recipes. If Professor Mansur talked about agents in multi-agent settings where you have different agents working together and you have this bird's eye view of these agents. In my work, mostly you look at the egocentric perspective where you are one agent and you have a different agent that you're trying to infer their goal. So if I'm going into my kitchen in my house and I see my husband breaking some eggs and melting some chocolate, these are my observations. I know that my husband only makes recipes from a specific recipe book that he likes. That's my recipes. I can infer that he's gonna make us a chocolate babka for Shabbat. So this is basically the problem that I want to be able to solve. Traditionally, this problem has been solved using planning, symbolic AI approaches. It's the AI that's usually you see less in AI Week recently. But it's still part of AI. And fundamentally, they were able to solve this problem very efficiently. If you have this representation of a domain, you have 3 different goals. The agent starts from the bottom left. You got these observations. Which goal do you think this agent is going to? G2, yeah. As people, we see this. It's very easy for us. So this is our domain theory. This is what can happen in the world, the fact that we can go left, right, up, and different goals. These are the observations that we got, and we are able to infer that. The way that goal recognition as planning works, it needs to take 2 plans per goal, one that goes through the observations, one that does not, and see the difference between them. And intuitively, if you think about it, if these plans are further apart, which means that you have to go through the observations that you've seen, then the cost between these 2 different plans for a specific goal makes one goal to be more likely than the other. And that's the way they basically solve this problem. So the way they do it is when you have, so we start with general raw data of someone in the kitchen. This is not my husband. And we need to perform some prior activity recognition to compress this into symbolic symbols. For example, fry egg. All we got from this eventually is just fry egg. Someone hand-coded this domain into the recipe book that we talked about. So in planning, this recipe book is called PDDL. And this is how it looks if you've never seen one. And now we have this, someone hand-coded this. We have this observation. We need to run the planners, like we said, planners or parsers, different approaches. And eventually we'll get from the other end of our machine this conclusion that this person is making breakfast. This is all well, but when we talk about this traditional problem of goal recognition, it's very costly, this domain description. And if you think that these PDDLs are nasty, try and compile things using CCGs, combinatorial categorical grammars. It's not pleasant. And this is most of the bottleneck of why these approaches remain less common today. You need a lot of workforce to design these. Also, because you only design what should happen, you don't represent what shouldn't happen. And then, for example, if you see someone with some noisy observation does something that you did not expect, you don't know how far away from the right plan that action is. And the online computation cost, the fact that you need to run in real-time planners to infer what is likely or less likely to happen. So I've been involved, I'm one of the authors of this work, goal recognition as reinforcement learning. And here's how we basically leveraged reinforcement learning to solve this problem. We took this previously known problem, this pipeline, and we replaced the domain theory with a set of policies and the goal recognition with a single measure. Now, what we do here, basically at the first stage, we use Q-learning or any other learning algorithms that you can use according to the problem that you have. And now you have different policies per goal. You have a policy for an agent that's about to make breakfast. You have a policy for a person who's about to make dinner, and one for someone who's gonna do the laundry, for example. And now when we get observations, the only thing we need is a single measure to tell us how likely it is to see this observation given this distribution. How likely is according to the distribution. So the nice part about that is that now it's still at a symbolic level here, but you can very easily take this and learn here policies that are based on a continuous state space and action spaces, and then you would get, you will alleviate the need to use activity recognizer as well. But let's just talk for a second about these two phases. So we start with learning the policies, and then we use a specific measure to compare between them. Our first implementation was Greco. We used tabular Q-learning to, we get states, actions, and the set of goals that the agent might be pursuing. We learned the domain theory that is no longer a PDDL or the cumbersome recipes that we've seen. Now it's a set of policies. And we use different metrics. We use max util, KL divergence, and divergence point to decide which goal is the most likely one. And we also get a distribution so we can rank them. We don't have to just output the best one. Basically, I won't go into this because I don't have much time. If you're interested, let me know. I'll talk to you offline. But the main point is that we just use a simple Q-learner that many of you are familiar with if you've worked with RL agents, to learn these Q functions. Nothing complex about that. The reward we designed, because it's a goal-oriented problem, goal-directed problems, was 1 at the goal, 0 otherwise. If we really wanted to be clever, we used a bit of hindsight. So given a trajectory of a good plan, we ran the planner once offline prior to the actual recognition task. And we could get a reward of 1 all along the way of our learner, and that really gave us fantastic policies to learn from. For the inference phase, we learned how to accumulate rewards using the Q functions, if you're familiar, the difference between different policies, or that we used the first point where we've seen an observation that diverges from the behavior that we'd expect from the policy. Given this fairly simple algorithm, it's not very sophisticated, we were able to take 3 traditional goal recognition problems, and only after 500 training episodes, not 5 million, 500 episodes, we were able to learn policies that were good enough to differentiate between goals that the agent might be pursuing here. And we got 210 goal recognition problems with varying levels of observability and noise. These are the results of the F-score for the traditional plan recognition as planning and R3 metrics. And you can see that in all domains, we were able to outperform this state of the art with very simple policies. And this is for the full observability. Once we get to partial observability and noise, results were even better than that. So we were able to reduce the cost by learning instead of coding the domain theory. This approach is robust to noise, and we didn't need any online runs of front parsers or planners. So that was a huge win. As a takeaway from this talk, what I want you to take from this work is that it really helps if you identify in your work why do you need RL? Who are the agents in your environment? What are the goals and the policies that you really need to learn, and how accurate do they need to be in practice? Leverage the fact that you understand these entities better to understand these relationships and understand the restrictions. And what other relationships can you use to improve the solutions that you offer, and what other problems could benefit from the solutions you've developed? So thank you for listening. I'll be happy to take your questions.
Thank you, Dr. Mirsky. Are there any questions? Please.
So, full recognition in a image for say there are multiple goals happening simultaneously. We have a kitchen, and unfortunately multiple cooks in the kitchen at once. You guys do any tests on that as well? I know it's a part of the problem, but I'm very curious.
So that's exciting. We have a couple of algorithms that are able to solve goal recognition with multiple goals. With reinforcement learning, it's very challenging because you do assume that you have a single reward function and you need to somehow compile different rewards and as different goals. So if they are in different places, for example, in a navigation problem, you can't encode properly that you should. So we have an ongoing project in my lab on universal functions for this purpose. Yeah, so we can talk later. Thank you. Okay. Absolutely. Yeah, so can we train an agent, use an agent online to improve the offline agent that was trained previously? Absolutely. This is one of the coolest things about using reinforcement learning for this problem. The fact that we now represent the policies using, we represent the goals using policies. Once we get a new observation or a new sequence, and we know that this person was pursuing goal number 1, in retrospect, we can improve this policy, right? So our model will just get better and better with time. Thank you. Yeah, so Peter Bill, Anka Dragan, Sergey Levin, the work that they've done on inverse reinforcement learning is about learning the reward function. We don't care about the reward. We know because it's a goal. It's a goal. Yeah, it's actually something that often people ask me when they hear about goal recognition for the first time. They ask me, so are you doing IRL? So it's like you can think about it as goal recognition is the online variant of IRL. In practice, you see a single sequence and you need to decide what's the goal that agent is pursuing. So that's the gap, but definitely there's a lot. You can use IRL as an approach to learn the policies here. Yes, thank you.
We don't have time for more questions. I see person. Any other questions? Okay. Very quickly. Okay. So, later. Thank you so much.